thin film interference. Another interesting effect caused by light's properties of refraction, reflection, and interference. It occurs when you have light passing through multiple media with different indices of refraction. Light first passes through a thin film. A thin film is a media layer with a thickness that ranges from 10 to the minus ninth to 10 to the minus 6 meters. That's pretty thin. Depending on the structure and materials of the media, the refracted light interferes with the partially reflected light to produce maxima and minima. The minima are where little to no reflection is seen, and the maxima are where wonderful colors and unique patterns are shown. Lens coatings are an example of destructive interference and are designed to reduce reflected glare. The glasses on the top do not have an anti-glare coating or thin film, and the reflection of the person standing above the glasses is seen. Perhaps there's his head, there's his eyes, and here's the light in the room. Okay? With the anti-glare coating, the light is transmitted mostly through the lens, and there is much less reflection. Can't see the guy anymore. This helps make photographs of people with glasses look better and enables you to see the person's eyes behind the glasses. The colors seen when a thin film is a layer of soap or oil are examples of constructive interference. Different colors are produced as the colors that make up white light refract at different angles. Nice soap bubble there and some oil on asphalt. It is helpful to refer back to the waves unit of this course to understand what happens to the light rays as they pass through different media. We'll review what happens with a pulse on a string that moves between strings with different densities. When a wave encounters a boundary, part of the wave is reflected and part of the wave is transmitted, just like light. So we're going to use this to help set up how light operates. So hopefully this is familiar. We have strings in each one of these 4 cases, and here we have a light piece of string connected up to a heavier piece of string. Here it's heavier, light, etc. So if you send a pulse on the light side here, right down to the heavy segment, what happens? Well, we drop to the bottom. Some goes through it, okay, and that stays in the upright position. The reflected pulse inverts. Okay, and if you need to review that, please go back to the waves unit. What if we have a more dense material where the wave starts here and then moves this way? Well, once again, you have a partially transmitted pulse along the light segment, and this time the partially reflected stays upright. It does not invert. So the transmitted pulse, to summarize the pictures here, is upright regardless of whether the new material is more dense or less dense. A pulse that remains upright is said to exhibit a zero phase shift. So this is zero phase shift. Okay, we're showing the same pictures now. And now let's look at the reflected pulse. The reflected pulse inverts when it encounters a denser medium, like over here. If the new medium is less dense, the reflected pulse stays upright. A pulse that inverts, turns upside down, experiences a 180-degree phase shift or a phase shift of lambda over 2. We'll use the same principles as we consider 2 cases of the transmission of light, film coating and bubble. So for a film coating, we have light coming in, and again, this is coming from the air, so we'll say n is equal to 1.0. It goes through a thin film layer. We've exaggerated the height there so you can see what's going on, with n equal 1.3, and then finally glass. So this would be your anti-glare coating on a pair of glasses. Notice how the index of refraction continues to increase. Then we're going to take a bubble. So let's see, here you have, once again, you're in the air, n is equal to 1.0. You go through a soap layer, that's your bubble, and then on the other side is air. So here what's going on? Index of refraction increases and then it decreases again going through the air. Consider a ray of light incident on a thin film over a second layer of greater index of refraction, glass in this case. This is the glass anti-glare example. The values of n increase with each layer. Index of refraction of air is less than the index refraction of the film, which is less than the index of refraction of the glass. The portion of the light wave that passes into the film layer, and that's shown by the red there, remains in phase. There is no phase shift for transmitted waves. That's the red arrow. The portion of the wave that reflects off of the film layer is phase shifted by lambda over 2 because the film has a higher index of refraction than air, and that's the green line right there. The reflected wave pulse shift is analogous to a pulse moving from a less dense to a more dense medium. So that would be the light string, then the pulse traveling into a heavier string. This happens again at the film-glass interface. That's this right here. The portion of the wave that passes into the glass layer remains in phase. There is no phase shift for transmitted waves. However, this wave is not involved in interference because it's not going to come back up here. And this is where the other person is observing what's going on. The portion of the wave that reflects off of the glass layer is phase shifted by lambda over 2 because the glass has a higher index of refraction than the film. And that's the green arrow right there. That's been phase shifted by lambda over 2. The ray reflected off the glass layer, the green arrow here, is finally transmitted back into the air. And notice how it comes to be parallel with the original reflected ray. Because here, coming down, it bent towards a normal. Here it bends away from normal in the same degree, so they're parallel once again. There is no additional phase shift here, but the lambda over 2 shift from the glass layer remains. So here's our reflected, and here's our refracted, then reflected, and then transmitted. The ray originally reflected, the blue arrow, and the ray reflected from the glass, the red arrow, are both in phase because they are both shifted the same amount. If the thickness of the film layer, that's this right here, got the T measured there, then the extra distance traveled by the second ray is a minimum of 2t depending on the angle of incidence. So why do we say minimum? Well, if it came straight down, right, it goes t here, and then it goes back up. That's another t, t plus t, 2t. But if it comes at an angle, it's covering a greater distance than that. So this will be the minimum distance, the minimum path length difference of those two waves. Now, if this extra distance is an integer multiple number of wavelengths, then what do we have? We have constructive interference. If the extra distance is an odd multiple of half wavelengths, then destructive interference occurs. Very important. The extra distance traveled occurs in the film, so the wavelength we have to use is lambda in the film. Lambda in the film is the wavelength we use for the equation. Here's where we show the brilliance of math and physics and how beautiful they work together. The words on the previous page said when you have a path length difference, in other words, this wave, the red one travels one distance, the blue one travels a smaller distance. So that distance there, which is going to be equal to this 2t, right, because the red one goes down then comes back up, that has to equal an integral number of the wavelength of the light in the film. That's exactly what this equation says without any sentences. And that gives you constructive interference. For destructive interference, we said it had to be an odd integer number of half wavelengths of the wavelength in the film. Now, one way to show that is just say, hey, it can only be 1, 3, 5. Another more elegant way is saying it's this. And you're going to let m equal 0, 1, 2, etc. for different orders of this. And in this case, let's see, if m is equal to 0, what do you get? You get 1/2. M is equal to 1, then you have 3 halves. Then you have 5 halves. And see, you've got these odd integers coming up here, each one multiplied by 1/2. The second type of thin film interference is similar to a soap bubble, where there is air above and below the thin film of soap. In this case, we have a ray of light incident on a thin film which is over a second layer of lower index of refraction. So N air is less than N soap, which also means that N soap is greater than N air. So you're going from N equal 1 to 1.25, then back to 1. We start off the same as in the film coating. The portion of the wave that passes into the soap layer remains in phase. There is no phase shift for the red arrow, the transmitted wave. The portion of the wave that reflects off of the film layer is phase shifted by lambda over 2 because the film has a higher index of refraction than air, and that's the green arrow. At the bottom of the soap layer, the portion of the wave that passes into the air remains in phase. There's no phase shift for transmitted waves. This wave is not involved in the interference. The portion of the wave that reflects off of the air at the bottom of the soap layer also remains in phase because the air's index of refraction is lower than the soap's, and that's the green arrow. The ray reflected off the bottom of the soap layer in green is finally transmitted back into the air as the red arrow. Again, there is no phase shift here because the ray is being transmitted. So the ray reflected off of the top of the soap, the blue arrow, and the ray reflected from the bottom of the soap, the red arrow, are out of phase because one has been phase shifted and the other one has not. Again, if the thickness of the soap layer is T, then the extra distance traveled by the second ray is a minimum of 2T. If this extra distance is an integer multiple number of wavelengths, then destructive interference occurs because of the phase shifting from the soap layer. If this extra distance is an odd multiple of half wavelengths, then the waves are shifted back into phase and constructive interference occurs. All that happens here from when we had the thin film is we just reverse the equations. For constructive interference, we've got that odd multiple of half wavelengths times lambda in the film. Remember, use the wavelength in the film, or in this case, the soap layer, and that will change from the wavelength in the air. The destructive interference, this time it's an integer number of the wavelength in the film, and m is equal to 0, 1, 2, 3, etc. for both cases. And now we put all that information on one slide. It's interesting to note, well, at least it was to me, hopefully it is to you also, I'm not telling you it should be interesting, I just find it interesting, that the equations for case 1 and case 2 are swapped for constructive and destructive interference. This is because of the different pattern in the indices of refraction for each case. With the film, n went from low to medium to high. For the bubble, low to high to low. And here's our equations. Constructive interference for film coating, constructive for the bubble. Destructive for film, destructive for bubble, and m ranges from 0, 1, 2, 3, etc. Light with a wavelength of 560 nanometers illuminates a soap film with an index of refraction of 1.4. What is the minimum thickness of the soap film in order to produce no reflection? We write down the givens, and automatically we transform nanometers into meters. But this time we really don't have to do that because our thickness will be in nanometers, and that will make sense for this type of problem because it's very thin. It's a thin film. We want no reflection. So we need the bubble destructive interference equation right here. 2T is m lambda film. So T is m lambda film over 2, right? We divide by 2, and that's pretty simple. Now we need to find lambda film. Lambda film is lambda air over n. We substitute in the givens, and we find that the wavelength in the film is 400 nanometers. Now sometimes you'll see this equation written like this. 2T is m lambda, where lambda is the air. And what has to be underneath that? Well, lambda film is lambda air over n. So you might see this equation, or 2nt equals m lambda. But here we're going to use the wavelength in the film. So we're using the proper equations there. So now we've got everything we need for this equation, and we'll substitute in, that's the lambda in the film of the light wave. And for m, we're going to set that equal to 1. That's the minimum thickness. M equals 0 would be the trivial case of no soap bubble. And like we said on the previous slide, we can leave the wavelength in nanometers as the thickness of the soap bubble can be measured in nanometers. So we get this answer, minimum thickness, 200 nanometers. Light with a wavelength of 650 nanometers illuminates the lenses in a pair of glasses with a thin anti-glare coating. The coating has an index of refraction of 1.3 and the glass has an index of refraction of 1.52. What is the minimum thickness of the coating that will provide for maximum transmission and minimum reflection? Which, if they're your glasses, that's what you're looking for. Since no reflection is required, the film coating destructive interference equation is the correct choice. That's 2t is n plus 1/2 times lambda film. So let's find lambda film first. It's lambda air over n. Here's our lambda in the air. Here's the index of refraction. So lambda film is 500 nanometers. And over here, we solved for t. We just divided everybody by 2. We bring the correct equation over from the other side where we've solved for t, and n is given for the glass block, but it's not used in the equation. It is only used to determine which equation to use. Since it is greater than the coating index of refraction, the correct equation was used. This is the glare equation, not the bubble one. So we substitute in the givens, and this time for a minimum thickness, we want the smallest number here. That will be when m is equal to 0. So that gives us the minimum thickness, and we multiply by lambda in the film, not lambda in the air, and we get 125 nanometers. Light with a wavelength of 660 nanometers illuminates a soap bubble with an index of refraction of 1.2. What is the minimum thickness of soap in order to produce maximum reflected light? Since a maximum reflection is required, the bubble constructive interference equation is the correct choice. So we solve for t by dividing both sides by 2, find the wavelength of the light in the film by lambda air over n. So it's 660 nanometers over 1.2, and we get a lambda film is 550 nanometers. We bring our equation over for t, and since we want the minimum thickness, we start with m is equal to 0. So then you have 0 plus 1/2 times 550 nanometers over 2, and the thickness, the minimum thickness, is 138 nanometers.